Hi, my name is Julia Silge, and I'm a data scientist and software engineer at Posit PBC. And today, in this screencast, we are going to be using this week's Tidy Tuesday dataset on Doctor Who, of whom I am a huge fan. I love Doctor Who so much, and I am actually currently rewatching seasons with one of my kids. So the timing is perfect. They chose this timing because there's the new Doctor starting, new episodes coming out very soon. Also very exciting. Specifically, what we are going to dig into is how do the ratings of an episode depend on the writer. Now, some writers have written a lot of episodes, and some writers have only written a few episodes. So we're going to use Empirical Bayes to estimate a rating for all of these different writers that takes into account the distribution of ratings and how many times we have observed each writer, i.e. how many episodes each writer has written. All right, let's get started.
Alrighty, time for Doctor Who. I am excited for the new episodes that are coming out because I am definitely a fan. Nope. There we go. What on earth? Okay, there we go. All right, so there are two data sets in here that I want to use. The first one is the episodes one, and then the second one is the writers one here. So I'm going to load both of those, and then let's look at what these look like. Whoops. So the episodes have, for all of these stories, story number has these variables here, and then the writers has for every story number who is the writer. So we've got information on the viewership, and back in 2021 I did a blog post about predicting the viewership, but I want us to look at rating this time, and I want to connect the rating to the writer. So the first thing we're going to do is we're going to join these things together. So let's say Doctor Who episodes. Whoops. Oh man. So you can tell I am using Copilot, and sometimes I do fight with it a little bit, which is interesting to notice. So I want to do writers, but I clearly cannot join it by writers here. So if I left join these together, it'll join by story number, which is what I in fact wanted to do. And so if I'll say group by writer, that's right. And then I'm gonna summarize, and I'm gonna say I do want N here. I'll do it like this. I want to know how many episodes each writer wrote. I do want a rating like this, like so. But then the other thing I want is a measure of the variance. So I'm gonna say, let's call it standard variance like this, and we're gonna take the variance of the rating, and then the variance of the rating, and I want to divide that by N, like this, like so. Okay. Rating, if we look here, rating is for some reason a character. So let's mutate rating as numeric rating, like that. All right, nice. So let's call this Doctor Who joined. So now what I have is, for every writer, for every writer of a Doctor Who episode, I have their name, how many episodes they wrote, the mean rating here, the mean rating. There's no NAs in this. The mean rating, and then the variance in that person's rating. So like this person has 29 episodes, and so their variance there is lower than this person who has 2. Notice we can't compute a variance for someone we just have 1 for, so we'll have to take that into account. All right, so let's look at how these ratings are distributed. Let's say Doctor Who joined. Let's put N on the x-axis and rating on the y-axis, and then we're going to say geom point, like that, and we will make this plot. Okay, so what is this plot telling us? On the x-axis is the number of ratings that the number of episodes that a given writer has been involved with. So here's this person over here, tons of episodes. And then over here are these writers who only wrote, 1 or 2 or just a couple episodes here. So when I look at this, let's look at these 2 in the middle. These 2 guys in the middle. They both have written quite a few. And so I feel pretty confident that the person up here with the higher rating actually does, I have more confidence in this comparison. Like this person's episodes are probably truly do, like this seems like a a real effect to me, that this one has higher ratings than this one. When I get over here and I look at all these writers that have only a couple of episodes, I'm not so sure that these are different from each other. Especially like, is this one way down here? Like, do we have, how strong is our evidence that this is actually a lower rated, like a worse writer than someone here in the middle? And this is exactly the kind of question that Empirical Bayes can help you answer, can help us understand. If we have data like this, we can use the distribution to compute what we call, or what people call, a shrinkage factor. Like how much do we shrink the outliers here in towards the middle based on how many times we measured them. So we can get better evidence about a better estimate of how different these are. So Empirical Bayes, what that means is that instead of just saying what a prior is, like deciding what my prior will be, we use the data that we have, this data right here, to make a prior. And then that's the prior that we use with Bayes' theorem to adjust and get to our posterior distribution. So let's make our prior distribution. This is, let's look at the distribution just in a histogram. So we're going to say histogram. I'm going to put the rating, and then I want to look at the density like this, because that will be better. There. Okay. Whoops. One more. Whoops, I did not do that right. AES. There we go. Okay. So here is the distribution of the ratings. We have a big pile here, kind of in the middle, and then kind of a fairly longish tail to the low side, and it doesn't really go super high. It doesn't go as high as it goes low. So, we have a lot of options that we could use to fit a distribution, fit some kind of, probability distribution to this, but let's just go like super, super dead simple, and let's just fit a normal distribution to this. Is it totally normal? No, but it is. I think we're just going to do something very basic here. So I'm going to find for this, for my prior here, that one is right. Yes. So my prior, the variance here, I'm going to say variance. Yep, same thing here. And then I can put this on my plot. I'm going to use stat function like that. And oh my goodness. Yes, dnorm, that's right. Args, mean equals prior mu, SD equals square root of prior var, that's right. And then certainly I do not want it to be red. There we go. So let's look at this. Size, so this should be line width. And let us make this a little lighter. And let's make this dashed. Okay, so this is the prior distribution that I learned from my data. Very, you have a lot of options of what to do here. And actually, if you had more data than this, you could do quite a good job of building a prior distribution. We just have how many? There are only like 40 of these writers, so we only have 40 counts here, and so I think this is good enough. I think this is good enough here. Certainly, we could there's a practically infinite set of options we could use for what to use here instead of the normal distribution. And all we would have to do if you pick something fancier would be to fit your data to the distribution and learn the parameters for the distribution that you're using. Okay, so this is the first part. We found the prior distribution using empirical Bayes, which what that means is we learned it from the data here. We learned it from the data. And now we can find out, we can do the posterior distribution, which is where the shrinkage happens. So what we want to do is, let's say Doctor Who joined, and we are going to compute two things. We're going to compute like a shrinkage factor. Oh gosh, I don't think any of those are right. Shrinkage. So here we want to put, that one is right. That one is right. So we want the variance of the prior, which is this really broad thing here, divided by us adding together. Remember, these are all squared. These are all squared. The prior plus for each writer, their variance. So we're going to add together the variance of the prior together with the variance of the for each writer. So this gives us the shrinkage factor, and then we can do the shrinking. We can take the rating. Let's say we're going to take the rating, and we are going to take that is, I don't think that's quite right. I think we multiply. I think it's got it switched. That's switched. So this needs to be rating, and this one needs to be prior mu. So this is Bayes' theorem, right? Like this is Bayes' theorem right here, where we can update our probability using our prior. So we observe, we have a prior, then we observe a rating, and then we can update the rating using the using that factor there. So let's call this Doctor Who empirical. Let's go here. And so what do these look like now? So the let's look at this one who has, we have 29 episodes, so the variance is low, and so this shrinkage factor is close to 1. This one's exactly 1 because the variance is 0. So we don't, and then we update it. So let's notice what happened for this first person. This is the observed mean rating, and then this is the empirical Bayes rating estimate that we learn using the distribution of ratings as a whole, and then we take into account how much variance there is here. So it moved just a tiny bit, right? It just moved a tiny bit higher. This person moved a lot higher. Their estimate of their rating moved a lot higher because we have many fewer measurements, many fewer episodes of how highly or low ratings that rating gets. And so here is something more, also a small move because the variance is again quite low, and so forth. So we did it. We did empirical Bayes. I mean, it's pretty. I mean, this math is not hard, right? Like this is pretty basic here. So notice we can't do it for the writers we only have 1 episode for because we can't compute the variance there. This is like a dead simple approach to empirical Bayes that I think is, it's actually useful in real life. Like this is an actually useful thing to know how to do, partly because it is so dead simple, and but it does have, of course, there's just kind of an infinity level of more complex work that we could do here, but that's a limitation of what we have. So let's make a visualization here. I'm going to put the rating, the observed rating on the x-axis, and then the shrunk rating, this is the empirical Bayes rating, on the y-axis like this. And then I am going to put points. Let's make the points have a certain size like this, so we can see which ones have a lot and which ones only have a few. And let us, you know what, I have these up here, but why don't I have a point one? Let's make a point like that. Okay. Okay, nice. So we can see where these all are. Let's put a diagonal, like a slope equals 1 line on this there. So we're going to say slope equals 1, something like, sure, and something like this. So this is the slope equals 1 line right here. Let's zoom in a little bit so we can look at this better. So if there was no shrinkage, if the rating that we observed is the same as the one that the rating that empirical Bayes estimated, it would be exactly on the line. So look at how the ones near the middle are on the line because they are around the mean. So they're like, oh yeah, that's about what we expect for any given writer. They're going to be there in the mean. Let's look at the writers that have lower ratings, the lower ratings one. Notice that they're all above the line. That means that once we applied empirical Bayes, they were increased. So they were pulled up towards the mean. And notice how the little dots are pulled up more than this big dot. This big dot is not pulled up as much because we have a lot more measurements of that writer's ratings. There are a lot more episodes from that writer, and so it is not pulled up as much because it's like we have more evidence that that's really where that writer should be. Let's look up here at the high values. These are mostly all below the line, and so that means that the empirical Bayes has shrunk them down closer to the mean. It has decreased their ratings. And again, notice that the ones that have a small number are pulled more than the ones that have the big numbers. Like these big ones right here are not pulled down very much. Because we have more evidence there. So that's exactly what Empirical Bayes does. And it is so useful because in our real life data situations, right, like how it is basically happens all the time that you have a lot of measurements for some things and much fewer measurements for other things, but we need to be able to use those measurements to do something. So this lets you not be super skewed by things that are out here in a way that is mathematically very straightforward and, does not take a lot of time to train some complicated model or, it's quite straightforward. I am interested in who these people are. So let's see. Let me load GG Repel. Such a nice package. I love it. And let us use geom text repel. And we're going to say the label is equal to, what's it called? Writer. Writer, yes, writer. And no, I don't want to bump the size up. I do, though. I'm using a special theme. And so I want the fonts to match. And you have to do that manually. So I'll put that in here. Well, we have to put it in like that manually. Okay. All right. Oh, okay. I just want to highlight again which ones were taken out. The ones with only one, the writers with only one episode, because we cannot compute the variance for them. Okay. All right. This is pretty interesting. All right. So here is Russell T. Davies. Here's Stephen Moffat, Russell T. Davies, higher than Stephen Moffat. Love it. I actually am not sure who Chris Chibnall is. I'll need to look that up. I don't know who this person is, but quite remarkable. Like this is a big spread here. I also am going to have to look up Gareth Roberts. I don't know who that is either. So this is interesting. I would love to learn more about, some of these people. Okay. This is an interesting case. Look at Neil Gaiman. Neil Gaiman is probably one of the furthest away from the line here. Maybe the same as Stephen Greenhorn here. But Neil Gaiman is far away from the line, meaning Neil Gaiman's real ratings are very high. Relative to the mean and what we might expect, if he's just sort of an average writer. So I guess I have a personal prior that Neil Gaiman's not an average writer, right? And so like I could somehow incorporate this knowledge into my prior, I'd be like, no, don't shrinkage those episodes. Those should be right on the line. They are great. If Neil Gaiman wrote more, they'd be fantastic also. So this gives you kind of an idea of how Empirical Bayes works, and I hope you can see how really useful this is in real life applications.
All right, we did it. Now, I've written about Doctor Who before. I've written about Empirical Bayes before. So I will include links to both of those in my blog post. But this is the first time I have written about Empirical Bayes for Doctor Who. So very big day, very exciting screencast here. I just want to emphasize again how this very kind of simple implementation of Empirical Bayes, how practically useful it is in real life data analysis situations. And it is so useful because it is very low overhead, very it does not take a long time to train some kind of fancy machine learning model, and it really can improve results from, some system where you're trying to do something based on, the ratio of something or how often you've seen something or some results you get when it is different, how often you have seen it from different people. So I hope this was helpful, and I'll see you next time.